In today's video, we're going to be talking about types of quadrilaterals, specifically focusing on Saccheri and Lambert quadrilaterals. But before we do that, let's do some review. Let's first look at the definition of collinear. 3 points A, B, and C are said to be collinear if there exists one line L such that all 3 of the points A, B, and C all lie on L. The points are non-collinear if there is no such line L. Now let's draw this out to make this more clear. We have points A, points B, and C. Now our line is going to be a line that crosses through A and B, and as you can see, C is not lying on the same line. That makes these points collinear. Now let's look at the definition of quadrilateral. Let A, B, C, and D be 4 points, no 3 of which are collinear. Suppose further that any 2 of the segments AB, BC, CD, and DA either have no point in common or have only one endpoint in common. If those conditions are satisfied, then these points determine a quadrilateral, which we'll denote by quadrilateral ABCD. Again, let's draw this out to make this more clear. So I'm going to draw the segment AB, and then BC, and then CD, and DA. And as you can see, this follows all the conditions listed, making this a quadrilateral. Now let's look at the definition of a right angle. Angle BAC is a right angle if the measure of that angle is equal to 90 degrees. Now you may have seen this before, and how we denote this in an angle is by drawing a box, like so. So this angle BAC, which measures 90 degrees, is a right angle. Now the last definition we're going to be looking at is the definition of parallel lines. 2 lines L and M are said to be parallel if there is no point P such that P lies on both L and M. The notation for parallelism is L parallel to M. Now to draw this out, we're going to draw 2 lines and they're going to be going in the same direction. That's what you're going to be seeing when you're looking at parallel lines. In this way, they will never intersect with each other, which makes them parallel. Moving on, now we're going to be looking at quadrilaterals, starting with one you've most likely seen before, a rectangle. A rectangle is a quadrilateral, each of whose angles is a right angle. Now what does that look like? Let's draw it. We have points A, B, C, and D. Now I've connected these, all their segments, and I'm going to be drawing a box around each angle, designating all of these 4 angles as right angles. That's what makes it a rectangle. Now let's look at some of the properties of a rectangle. Well, first we know that all 4 angles are right angles, but there's more to it. As you can see, we're going to be having parallel lines between the segments. So segment AD is parallel to segment BC, and DC is similarly parallel to segment AB. Now that also shows congruence that we can see in the image. AD is congruent to BC, and DC is again congruent to AB. All right, let's move on. Now let's look at a Saccheri quadrilateral, which is one you may not have seen before. A Saccheri quadrilateral is a quadrilateral, ABCD, such that angle ABC and angle DAB are right angles, and segment AD is congruent to segment BC. The segment AB is going to be called the base of this quadrilateral, and the segment CD is going to be called the summit. Now hang with me as we get to this definition because I will be drawing it soon, and it will really clear things up. Lastly, the two right angles ABC and DAB are called the base angles, and the angles CDA and BCD are called the summit angles. So again, let's draw this. We have point A tied to point B. I'm going to draw point C up here and draw point D up here, not connecting C and D yet. But as we know, angle DAB is a right angle and angle ABC is a right angle as mentioned in the definition. And we know that AD is congruent to BC. Now in this quadrilateral, we're going to see a curve connecting C and D. And we call this the summit. And then the bottom segment, AB, is the base. So let's look into some of these properties. As we know, DAB and ABC are right angles, and AD is congruent to BC. Now, what else can we see? We can also see that AD is parallel to BC. Okay, let's move on. Let's look at a Lambert quadrilateral, another one you may not have seen. A Lambert quadrilateral is simple. It's a quadrilateral in which 3 of the angles are right angles. So again, let's draw this. Starting with A, and then going to B, going up to C, and I'm going to draw D a little bit out here. Now, I'm going to connect these, and you're going to see again, it's a little bit of a curve, and that's where we get these 3 right angles. So again, let's look at the properties. Angle DAB, angle ABC, and angle BCD are all right angles. And that's all the properties we're going to see with this one. Now let's compare and contrast. Let's start with right angles. For a rectangle, as we saw, they have 4 right angles. For Lambert quadrilaterals, we have 3 right angles. And for Saccheri, we have 2 right angles. Seems easy enough to remember. Now, when we're looking at congruent segments, rectangles have 2 pairs of congruent segments. When looking at Lambert, there are no pairs of congruent segments. But for Saccheri, there is 1 pair of congruent segments. Now looking at parallel segments. For rectangles, there are 2 pairs of parallel segments. For Lambert quadrilaterals, there are again no pairs of parallel segments. And lastly, for Saccheri, there is 1 pair of parallel segments. Okay, so what is the common factor within all of these different quadrilaterals? It's right angles. Each of them have at least 2 right angles, and that's the commonality you're going to see with any of these quadrilaterals. Depending on what geometry you're using in the future, you may see any of these quadrilaterals, and I hope this video helped you understand the difference. All right. Thank you so much for watching this video, and I hope you better understand the different types of quadrilaterals.